Okay, here we are once again at the physics video lecture. Physics 2A, video lecture 41. So I've brought a few demonstrations here. Let me tell you what it's all about. We're still talking about thermal physics. And we ended last time with entropy, with solar energy. But I'm going to go back to the idea of the mechanical equivalent of heat. So once again, thermal physics. And I'll review this equation that we call the mechanical equivalent of heat. And that's what we're going to take off with. So I'm not following chapter 12 at all. Okay, we're going to cover what's essential in it, but this presentation is much, much better. Okay, so once again, we go to the mechanical equivalent of heat, which, as you recall, is an equation. And that equation is that 1 calorie, kilocalorie there, food calorie, write that down correctly, is equal to 4,186 joules. And heat here, our thermal energy, the calorie, remember the calorie in the butter candle, for instance, and we saw that we could convert that, or we could equate it with this 4,186 joules. Now, when we did that, we actually did friction, and we did from work to heat. So via friction and the joule churn, or you can just rub your hands together, you're doing work and your hands get warm. So what we've so far, you can say we have work being converted into thermal energy. Now, the next question is, can we reverse this arrow? Can we take thermal energy, so and so many calories, and convert it into work? And that's what this chapter for us is primarily going to be about, taking thermal energy, call it heat, and converting it to useful work. So far we had this. Next, can we convert thermal energy to work? And of course we can, but we want to study that. Work, question mark, right? Then it would be turn thermal energy into work. And remember, this calorie was our good old butter candle for starters, so we'll draw this thing once again. Little red, and we had a beaker of water, on a stand, and we had a thermometer inside. So that was our thermal energy. Now, this butter candle is never going to produce work if we're just using it to heat water. So we need some kind of mechanism to turn the thermal energy, and this is actual energy, calories, they're joules, but we need some kind of mechanism to obtain work. So we need a mechanism. And I brought a couple mechanisms, a couple machines to class. And wish me luck on this, right? One take, no edit. This thing here is a Christmas pyramid. It's called a Christmas pyramid. I'll write that down, draw a little picture. It has candles here. They burn down pretty much, but we're going to use them anyway. And there's a little nativity scene, and the candles are going to get some convection going through the turbine here, and it's going to spin around. The problem is this room has enough draft in it that when I release this thing, it will rotate on its own, but that won't stop us from making our point. Okay, if the wind kicks up, this thing will rotate alone without the candles. about to start. But anyway, I'm going to demonstrate that because I have a little trick up my sleeve. So definitely the candles are not butter, but they represent thermal energy. This thing is really cranking. So we're gonna light the candles, and I've got a way to make this thing do what I want it to. But yeah, the breeze in here is astounding. Okay, let's not start a fire. Okay. Okay, here's what we do. We add a chimney to the mix. And the chimney effect, this is just a rolled up tube of paper. The chimney effect is going to make my point for me. So let's see here. Okay, so I take this tube and I've got a chimney. I lower the chimney. Oops. Lower the chimney. And the effect is that we're going to get some serious speed. You guys know what you want for Christmas. Okay, so it's really zooming. I can even see that. I'm trying not to get a fire here. And the reason is that the chimney allows us to get a really controlled convection, which will overcome the effect of whatever's going on in the room. There we go. Okay, I'm going to declare victory as a success. So yeah, that's the Christmas pyramid. And go ahead and look some of these up online. You'll see some really big ornate ones. It's a European thing. Good, so I'm going to write that down as our next. Stop this thing from being a distraction. There we go. So I'm going to write that down as our next topic and demonstration. Well, demonstration that we just had. So the example of converting thermal energy to work, in fact, this is the newest of the new. This is a turbine, okay? So, demonstration, Christmas pyramid. So you get a picture of this for your notes. Why not? You'll see they have big double-decker, triple-decker, everything. Good, so the Christmas pyramid has the candles down here. Right. And then there is the platform for the turbine, that propeller there. And there's some kind of machine here. In our case, it was the nativity scene that's being carried around in a circle, and that represents useful work. So, here's our flame. And since we know about convection, we know that there's actually an air current here. The hot air is rising. And that's what's driving the thing. So you get the fuel, you get the hot air, it rises, you get a convection current, and this thing rotates. Now the chimney is a really crucial piece of this equipment. So I'll just indicate the chimney like that. What the chimney does is isolate a hotter and a colder area. And remember, convection goes, is due to a temperature difference. And what this does is it really makes a properly localized high temperature and low temperature. So I'm even going to write here, down here we have TH, and up here we have TC, right? Higher and lower temperature. That's the Christmas pyramid, fuel in the candles, okay? And then we have hot air rises. And then we have the chimney effect. which really gives us substantial air current. And the whole thing is we get the work. So there's our machine, and we can harness that. The second example I have is a steam engine. It's a model steam engine that really works. And I'm gonna ignite some fuel, put it in here. This little boiler has water in it. There's a little cylinder with piston, and it'll turn this flywheel, and if we're lucky, this little light will even go on, okay? So I'm just going to demonstrate that, and then we'll start analyzing this stuff. Let's see, I brought the torch to make short work of igniting the fuel. Okay, so there we go. Got a flame, put that under there. And then we have to be have a little patience. So while that is happening, we can use this side of the board to talk about the steam engine. So this was the Christmas pyramid, that's our one example. And the second example is the steam engine. And while I'm at it, I'll just show you what this device is. This is a demonstration of the conversion of circular motion to linear motion. Okay, so I can turn a handle here, and these little golf balls just easy to fall. So I can turn a handle on this side, and I've got the rotational motion. That's what this part is going to do on our steam engine. It's converted to this linear reciprocating motion. Now on our steam engine, the machine is pushing this. So the machine's providing the reciprocating motion, and it's turning it into rotational motion. So this is an interesting demo, built in our very own machine shop. Okay, so I'll put that back here. And the steam engine's about to do it. Give it a little kick. And away we go. And we even have the light. I'm going to hold this up to the camera while we're getting this good. Okay, fantastic. Everybody knows what they want for Christmas. So how do we turn this thing off? Well, it doesn't have an on-off switch. Actually an important point in its own right, so we just got to blow it out. Oh, that's the fire department didn't come. A little smoke there. And now the residual steam is gone. And there's one thing I did not show you guys too late. You may have seen it. There were puffs of steam coming out when I had it held this way, and those puffs of steam occur because the cylinder here, very small to see, but cylinder pivots up and down and covers and uncovers a little valve. So the presence of a valve in here to release steam is very important. Be that as it may, a fully functioning steam engine, which you can look up and learn all about, and we have it attached to a generator which made this little light bulb go on. That's modern civilization in a nutshell. Okay. Yeah, in fact, that's one aspect of the work that you're going to talk about next semester when you learn about electricity and magnetism, how a generator works, and eventually makes that light bulb go on. But the rotation and the was already worked. Good, so let's go ahead and say a little bit about the steam engine. So the steam engine has fuel burning, as you saw. Do a little producing the flames. And there is that tank there. It's got a window in one end, and it allows you to see that there's a little water inside here. Okay. So you're boiling that water and producing the gas. And in that machine, we've got that cylinder just on top of the tank itself, or the boiler, I should say. But typically, you'll take some kind of pipe to connect it to a cylinder with a piston inside. And there's a connecting rod that attaches to a flywheel. I'll write all those words down. Attaches to a flywheel, and you can get that rotational motion. So what do we have? We have the fuel, and then we have the boiler. Okay. And there is pressure on steam under pressure. And that steam under pressure is what's going to push the piston. So first of all, there's the cylinder. The piston is inside. We have the connecting rod and the flywheel. And there's my picture. You guys can find better pictures. And then this thing here, which is going to rotate, is the flywheel. Well, there's one missing ingredient. Let me check how we're doing time-wise here. Fantastic. One missing ingredient, and that is the valve. So we have to have a valve here. Let's put it in a different color. We have to have some kind of valve, and it actually has to be connected mechanically. In the simplest machine, it has to be connected mechanically, but it definitely has to open and close with the proper timing. So put a valve here, very important, and the valve releases, it opens and closes and releases some steam. I'll give it a little releasing of steam right there. Okay. Good. So those are the two heat engines that we're going to start with. I could say a little more before I erase this. Yeah, here's the important point. So just as we had with the reciprocating motion, turning and rotational motion here, this piston is going to be pushed forwards and cause that wheel to rotate. So it gets pushed all the way, and you have a half a turn. Now, you want it to actually do a complete turn, and you're up against the problem of there's too much pressure in there. So it did some work on the half turn, and you're going to have to do the same amount of work on the second half turn to get it back. You're pushing against resistance. That's why we have the valve. So on the return stroke there, the valve opens, the steam evacuates, and under less pressure, and then you're back where you started, the valve closes, and steam pushes the piston forward. Okay. So that's the functioning of the steam engine, and those are its essential parts, and there's a nice model. Get one for Christmas. Okay, what we're going to do next is analyze this a little bit further. Analyze it a bit further, because what we have to see is that this completely different type of steam engine, or heat engine I should say, can be shown to have the same principles at base as this one right here, as a steam engine. So what are those principles? The principles are that we're burning fuel, so we have the heat here, Q, and we have a higher and a lower temperature regime. And that is present here as well. So we're burning fuel, releasing heat, and there's high temperature. And in this case, the high temperature, we could say, is in the boiler, and the low temperature is the atmosphere. So TC, the surrounding atmosphere. Okay, you guys can make this a lot better in your notes. Leave some room, put room for everything here. And good. This temperature difference is a crucial aspect. You really saw it with the chimney effect that I just erased, and it will play a major role. So I'm going to erase this and make a little, repeat the drawing actually, but so what we have now are heat engines. I've shown you two different types. The purpose of them is to take thermal energy and turn it into useful work. Okay, so thermal energy to work, or we could say Q to work. That's our goal. And I had that mechanical equivalent of heat up there. I'll just remind you, there's a lot of work to be had if we could succeed in turning the energy and the fuel into work. 4,186 joules per calorie, that's a fair amount. Good. The different types, we had the Christmas pyramid, which I'm not going to draw again, but we can list that. And we had the steam engine. And the steam engine was what's called an external combustion. The third type, just a regular motor or engine, say in a car, not only a car, but as an example, lawnmower, okay, is internal combustion. We'll do a little sketch for this. So our external combustion, remember we piped in, so we had water in this boiler and we piped it into the cylinder, okay? So that's where the external combustion was, the cylinder was here. For internal combustion, we'll have our cylinder with the piston inside, okay, connecting rod, flywheel, and the combustion happens in here, and then a little bit of gasoline is squirted into the cylinder and ignited with the spark plug. Okay, so gasoline is gasoline is injected. So that's referred to as fuel injection on your engine, and ignited by the spark plug. So in that case, that TH that I was talking about, the high temperature, you know, here it was in the boiler and in the cylinder. Here there is no boiler. Okay. So the temperature that results from the ignition of the gasoline is right there in the cylinder. It's an expanding gas and it pushes the piston forward, and it happens so many times per second. So we've got the external combustion, internal combustion. They're both heat engines though, and you know, we're using fuel, getting useful work out of it. Okay, so from there I'll check the time for a moment. I'll start a little bit of an analysis of this. Or here's what I'll do instead. This is actually a good place to stop. We'll start in with the analysis next time. As far as your homework goes for this particular little section, it's just the notes. And so there won't be a problem set here. You just got your notes plus some images. Okay, the stuff that I just sketched here, what you want to do is download some images, print them out, put them in your notes, and then when you turn in your notes, show me, of course, that you have them. Okay. So images of the Christmas pyramid, the steam engine, other relevant engines, up to the thing that we've discussed here. So you have a little pictorial material in your notes. Good. This is a good place to stop here. What we're going to do after this is take the features that we've discussed here and that we've seen in our demonstrations and do an abstract, very typical analysis, and we're going to bring in the entropy. Okay, so that entropy discussion, which was very abstract, is going to play a central role in analyzing the heat engine. Okay. So that's good. I think we're at a good spot here. Everybody enjoy their Thanksgiving, and we'll see you next time.